In this video, I'll talk about the internal energy. The internal energy of a system is the sum of the kinetic and potential energies of all of the particles that compose the system. What about the internal energy of the surroundings of the system? Very simple. It's just the sum of the kinetic and the potential energies of the particles that compose the surroundings. The U-pack notation for internal energy is U. However, you'll see both E and U in many chemistry and physics textbooks. What's the difference between the internal energy and energy? When we are talking about internal energy, the kinetic and the potential energies of a system as a whole relative to its surroundings is not part of the internal energy. For example, when you throw a baseball up, its potential energy increases, its kinetic energy increases, but its internal energy remains unchanged because the motion of the baseball as a whole is not counted as part of the internal energy. The height of the baseball as a whole is not counted as part of the internal energy either. But what's the internal energy of the baseball then? The baseball is composed of many atoms. These atoms vibrate. These atoms attract and repel each other. Therefore, the internal energy is simply the sum of the kinetic energy of the atoms within the baseball and the attraction between the atoms in the baseball plus the repulsion between the atoms in the baseball. How can those atoms attract and repel each other? Very simple. Each atom consists of at least one electron and one nucleus. If you have two atoms, the two nuclei of these two atoms repel each other. The two electrons of the two, let's say, hydrogen atoms repel each other. At the same time, the two nuclei are attracted to the two electrons in two hydrogen atoms. Even within just one single atom, you have kinetic energy of electrons, kinetic energy of the nucleus, and also you have repulsion between the electrons, and you have attraction between the nucleus and the electrons. Internal energy is a state function. The value of a state function only depends on the state of the system, not on how the system arrives at that state. More examples of state functions are temperature. If you say right now the room temperature is 25 degrees Celsius, it is 25 degrees Celsius depending on the room's current state. How has the room temperature arrived 25 degrees Celsius? From 30 or from 10, it doesn't matter. The current temperature is 25 degrees Celsius. That's a state function. Pressure is a state function. Volume is a state function. Your height, weight, and age are also state functions. When a system changes from its initial state to its final state, the change of the internal energy is very simple. It's the final internal energy minus the initial internal energy. And the change is denoted by this uppercase delta sign. Delta E equals E final minus E initial. The first law of thermodynamics tells us the energy of the universe is conserved. Therefore, we can write this in terms of an equation. The change of the energy of the universe is equal to 0. And this is always true. This is my diagram of the universe. And let's say we are investigating this system, this blue star. This is my system. The rest of the universe is called the surroundings of this system. Between the system and the surroundings, there might be heat flow, and work might be done by the surroundings to the system or by the system to the surroundings. Remember, the universe is equal to the system plus its surroundings. And because energy is additive, that means the energy of this universe is equal to the energy of the system plus the energy of the surroundings. We can have this equation. E sys refers to the energy or internal energy of the system. E sub SURR is the energy or the internal energy of the surroundings. Again, the change of the energy of the universe is always 0, and then we say the change of the sum of the system energy and the surrounding energy is always 0. The change of a sum is equal to the sum of the two separate changes. Therefore, we know delta E system plus delta E surroundings is always 0. And then we know the change of the internal energy of the system is equal to negative, the opposite of the change of the energy of the surroundings, and vice versa. For simplicity, we sometimes just write delta E instead of delta E sys as the internal energy of the system. As the change of the internal energy of the system. I forgot to mention this delta sign here. The internal energy of a system changes when heat flows into or out of the system. Or if work is done to the system or by the system, that will also change the internal energy. We can use a simple equation here. Delta E equals Q plus W to quantify the above statement. So again, this is a change of the internal energy of the system. This is the sum of the heat that flows into the system and the amount of work done to the system. And then you may ask, what if the system is doing work to its surroundings? What if heat flows out of the system? And then this Q and W will have negative signs. In summary, when heat flows into the system, Q is greater than 0. When heat flows out of the system, Q is less than 0. When work is done to the system, work is positive. When work is done by the system, work is negative. And actually, by looking at the relationship between the system and the surroundings, we can tell this. When heat flows into the system, Q is positive, and then Q of surroundings is negative. Heat flows from the surroundings to the system. And then when heat flows out of the system, it flows into the surroundings, and then Q sub surroundings is positive. Same here, when work is done to the system, we know work of the surroundings is negative. When work is done by the system, well, we know it's done to the surroundings, therefore work of the surroundings is positive.